Hi, everyone. Yeah, thanks for the invitation and thanks to the organizers. It's really great talk so far, so it's been a pleasure. So I'm going to talk about some joint work from late last year with Ahmed Alaoui, who's at Cornell, Ronen Eldan, who's at Microsoft, and his PhD student, Ariana Piana. And we're going to talk about dynamics, Glauber dynamics for random field Ising models. So let me just set things up, remind you of things you might know already. So the underlying geometry for me throughout the talk is going to be ZD, or subsets of ZD, and little n will be the index of the side length of the box that we're thinking about. So here's d equals 2, d equals to 3, n by n by n by n, dot, dot, dot box. And okay, so the Ising model, probably most of you are familiar with it. We've seen it a couple times this conference, I guess, is an assignment of plus or minus, and I'm going to use blue for plus and red for minus throughout, to the vertices of the finite graph that we're working on, where the probability of a specific configuration or assignment of plus and minus is given by the Gibbs measure, where the energy function, or h, the Hamiltonian, counts up the number of disagreements between neighboring sites. And I moved the beta onto the h, maybe a little unconventionally here. So beta is the inverse temperature parameter for this model. And of course, it's famous that in dimensions 2 and higher, there's a phase transition in the behavior of the model from disorder to order as you vary this beta parameter. So Glauber dynamics, so the Markov chain that we're thinking about, is a single site update local Markov chain, which, so I'm going to work in continuous time, so I don't have to drag around n to the d's everywhere, is I assign a rate 1 plus on clock to every vertex in my graph. And when the clock rings at a vertex, v, then I update the spin at the plus or minus at the site v, according to the conditional distribution given the remainder of the configuration. And because the interactions in this model are just nearest neighbor, that's the same as just resampling it conditionally on its 2D neighbors. So here's a picture. So the clock at this middle guy rings, and then I update it conditionally on the on these three, and that's going to be something like exponential, proportional to exponential 3 beta for the pluses and to go to plus, and exponential 1 beta to go to minus. Okay. So this has been studied since, I don't know, 60 years ago, I guess, at this point, both as just a Markov chain to sample from the Ising model, but also as like a physical model for the thermodynamic evolution out of equilibrium for statistical physics systems. And the upshot is that this Markov chain is easily checked to be reversible with respect to the stationary distribution, or with respect to the distribution that it's doing the updates with respect to. So in this case, the Ising distribution. Okay, so when we have a Markov chain and we're thinking about, one of the most, when we know what it's reversible with respect to, one of the most natural questions to ask is how fast does it converge to that equilibrium distribution, and specifically as a function of the size of your domain in this case. So to quantify the rate of convergence, I guess maybe the canonical way to quantify this is what's called the mixing time. So this is a total variation notion of equilibration from a worst case initialization. So I take the first time until the first time when, from a worst case initialization, my total variation distance to stationarity is less than a quarter, and a quarter is artificial because as soon as you're faster than that, then you converge exponentially fast to equilibrium. Okay. All right, so a different very related way of quantifying the rate of convergence is what's called the spectral gap. And so I guess we also saw this in Evita's talk yesterday. So the spectral gap, one way to define it is a variational form. So I say that the model has a Poincare inequality with a constant lambda if the variance of test functions is bounded by lambda inverse times the Dirichlet form. And okay, so the Dirichlet form, for those of you who don't know, it's basically, you can, if you like analysis, then something like this. where this gradient's taken with respect to the transition matrix P that you're working with. And the best constant I can put here is the spectral gap of the Markov chain. Alternatively, you can think about the spectral gap as the gap in the spectrum of the transition kernel for the Markov chain. So this is nice because it controls your convergence rate in the following sense. It tells you how fast test functions converge. So if I take the expectation of the value taken by a test function after t steps of the Markov chain, then it converges exponentially fast to its equilibrium value with rate that's given to me by the spectral gap. So once t is much larger than the inverse of the spectral gap, this is exponential decay, and you get really close to equilibrium. Okay, I know this is familiar for a lot of you. I just reminder, have everyone on the same page, and we're going to see a slightly different form of this later. So what's the point? The spectral gap controls the mixing time up to a factor of n in these kinds, or the number of vertices in these kinds of systems, and it's quantifying your exponential decay rate to stationarity. Okay. Are there any questions just about the background, I guess? Right.
So in Evita's talk, it was not the case. There was some problem. You couldn't use the spectral gap to the mixing time.
Well, she was trying to get cut off, which I guess is a much more refined notion than if I'm just trying to miss by a factor of n, but yes. That's right. Yeah. Yeah. So I mean, there's these two are within a factor of log of the worst probability in your state space of one another always. Okay. So what's known about the mixing time of the Ising model on subsets of ZD? There's a phase transition that corresponds to the equilibrium phase transition of the model. And okay, there's a couple of things I want to emphasize. So at high temperature, it's well known now that there's optimal order log n mixing and order 1 spectral gap. And in fact, you have cutoff, and this is the order of the mixing time was shown by Martinelli Olivieri, the log Sobolev inequality by Chesi, and then the cutoff by Allen and A. L. Lubetsky. And these kinds of things rely on some implication from some decorrelation estimates on the model at equilibrium being implying mixing time for the dynamics. So that's sometimes called weak and strong spatial mixing, and we'll see things like that in more precise notions later. At criticality, you get polynomial mixing. This is open in dimensions 3 and 4. And once you're low temperature, then you get slow mixing, exponential in n to the d minus 1, which is the cut width of the box that's n by n by n, because this is how long it takes to go from mostly plus to mostly minus, which are your two modes. But we're really going to be focused on high temperature behavior in this talk. Okay. Any questions about that? All right. So now let me talk about the model that the actual talk is about, so the random field Ising model. So in the random field Ising model, I add a random external field to every site on the lattice. And these fields are IID, symmetric. You can think for yourself Gaussian if you want for the rest of the talk. Okay, so what that does is that it adds this linear term into the probability distribution. And here I've tried to make the lines thicker where it's a bigger field and thinner where it's a smaller field. And then the sign is telling you what the sign of the field on that vertex is. So, if it has a field of plus, it wants to be more plus, but it also has the interactions with its neighbors. Okay. So the random field Ising model has also been studied for a long, long time. And there's something, there's been a lot of interesting breakthroughs in the recent years on this model. So in particular, it was conjectured along, maybe 40 years ago by Imre and Ma, that in dimension 2, you should have exponential decay of correlations regardless of the temperature, as soon as you have a positive variance for your random field. So even at the temperatures that are really low, the introduction of an arbitrarily small random external field destroys the long-range order of the model and makes it have exponential decay of correlations. So this was in 2017, Shurav Chatterjee proved some kind of quantitative decay on the rate, and this kind of led to a sequence of works, and I guess I'll mention the culmination of this, which is the work of Ding and Xia, and also Ising, Menherel, and Peled. And so we know that there's exponential decay of correlations if the external field is Gaussian for any positive variance for every temperature. Okay. So indeed, in dimension 2, you're kind of always in a high temperature regime at least when you're thinking about decay of correlations. But I want to emphasize the field is random, so there might be regions where the field is very small just by chance. And in those regions, if you're low temperature without the field, then you don't have exponential decay of correlation. So that's why I wrote in expectation or for typical realizations of H. Okay? That'll be important. Okay. In dimension at D at least 3, there's a phase transition. So you preserve the long-range order at beta large when the variance of the random field is small. And so here's a picture to kind of show a phase diagram. So this bottom line is when there's no external field. When there's no external field in the high temperature regime of the Ising model, you're also high temperature for, red is for hot, so high temperature. You're also high temperature whenever you introduce an external field. And so this was a nice correlation inequality of Ding, San, and Sun, said that introducing an external field can't make you more ordered. You stay, if you had a decay of correlations, you maintain decay of correlations. And result of Ding, Liu, and Jia showed, actually, but this is really Imbri and Bricmont and Kupiainen showed for some regime here, shows that for any low temperature, if there's a sufficiently small variance such that long-range order is preserved. So you can go a little above this line. And if I add a strong enough external field, kind of crude arguments tell me I can destroy the long-range order. Okay, so what we're going to be thinking about a lot, or I guess where our results are most interesting, is this kind of regime over here, where without the external field, there is a long-range order, but the introduction of the external field means that you have a decay of correlations in general or in expectation, even though there might be small regions that are low temperature like. Yes?
What are the other colored regions?
These are predicted but not known, I guess. So crude arguments apply here. Here it should be, these two should be decay of correlations, but there's small regions where there's no decay and long-range order, but not proven. So this question marks, but expected.
And the curve is something that is just a sketch.
Yes, I don't know a function. I don't know that any function is predicted. Yeah. Okay. Any other questions? All right. So let me talk a little more about this region that I was saying is the most interesting. So this is sometimes called the Griffiths phase. And it's a regime where, as I said, in expectation or for a typical realization of H, you have exponential decay of correlations, uniqueness, high temperature behavior. But in an n by n box, by chance, there will be some small regions where the external field on like all the sites there are really small, let's say. And so things look low temperature locally. And so there you don't have any decay of correlations. And so I tried to be like, okay, notice that the fields that are, let's say, epsilon small forms a subcritical percolation. So even though it's not many of them, it's kind of all over the place. And then there are some highlighted regions where they're kind of atypically dense, and so you might get some low temperature behavior. Okay, so this leads to things like non-analyticity of the free energy, even though you're in a high temperature regime, some other issues like that. From the perspective of the dynamics, it means, on the one hand, standard arguments that show that fast spatial decorrelation or like decay of correlations implies fast mixing don't apply. And also, they really shouldn't apply because you can kind of encode a slowdown of the Markov chain into these small regions, at least to some extent. Okay, so it destroys traditional arguments, and also it slows down your dynamics a little. Okay, so this slows down the dynamics somewhat and destroys many standard approaches to bounding Glauber dynamics mixing time. So in a recent work, Tyler and several co-authors, showed that on general graphs, as long as the variance is sufficiently large compared to the temperature, then there's a polynomial time approximate sampling algorithm. So in this kind of crude arguments regime where the decay of correlations globally follows from these strong bonds, but you can have local regions of correlation, strong correlation, they show a polynomial time sampling algorithm. This isn't a Glauber dynamics, it's based on something like a White's tree to sample site by site. Right. So what the rest of this talk is going to be about is showing mixing time guarantees or spectral gap estimates for the Ising model throughout this region, I guess, under the assumption that this is the region. Okay, so let me define what the kind of assumptions of uniqueness are that imply mixing time estimates. So a kind of classical notion of spatial mixing or decorrelation that's used to get mixing time bounds is what's known as weak spatial mixing, which says that if I take a box with plus boundary and a box with minus boundary, then the TV distance at the root or in the middle between these two is decaying exponentially in the distance to the boundary. So this is just exponential decay of correlations as you would think of it traditionally. And I will ask for that in expectation. So I fix a box and I take an expectation over the random field and I ask for this to hold. Okay, by Markov, this also means that with high probability, if I take an R by R box, then it's such that the field is good. There's exponential decay of correlations. All right. So under this kind of assumption, for example, in Z2, this follows from this result that would establish the Imry-Ma phenomenon that you have exponential decay of correlations, so you have this weak spatial mixing and expectation for all temperatures and all positive variances. And in D at least 3, it should be throughout that yellow-orange region as well as the red region. Okay. So this is kind of a minimal assumption of high temperature behavior is how it's thought of. So then the theorem says that under the assumption of weak spatial mixing and expectation, so the law of H and beta are such that this holds, then if I take a n by n box, I have what's known as a weak Poincare inequality as opposed to the standard Poincare inequality with constant that's polynomial. The distinction is instead of having variances at most a polynomial times the Dirichlet form, I have a kind of Helder type, so a variance is at most n to the c, something like the L infinity of the test function raised to some fractional power, the Dirichlet form to some other fractional power. Okay, so this might not mean anything. So what does it imply? It implies that test functions, instead of decaying exponentially, I can guarantee that they decay polynomially to their expected value at stationarity on polynomial time scales. Okay, so this does not imply mixing time, because if I take the test function to be like a Dirac mass at a point times some exponentially large number, decaying an exponentially large thing by a polynomial on polynomial timescales doesn't make it small. But this actually has some history, these types of weak Poincare inequalities. For instance, they've been found to be the truth in certain critical interacting particle systems. So it was kind of interesting, and this is like work of Liggett in the 90s, and there's several other settings where they're the truth. I probably don't expect this to be the truth in the Ising model in this uniqueness regime, but yeah, so it was interesting to see this pop up. Some implications of this weak Poincare inequality are that if I take a warm start, where warm means my radon-nicodeme to stationarity is bounded by a polynomial, then I have polynomial time mixing from those kinds of initializations. And we can actually use that to get a Markov chain-based sampling algorithm by kind of building up the domain one site at a time, and then using the, if it's only one site smaller, it's a warm start with respect to one site added. Okay, so this is the results in this kind of minimal assumption of uniqueness. You have a weak Poincare inequality, algebraic decay on polynomial time scales, and sampling algorithm. Are there any questions about that? Okay. So a different kind of spatial decorrelation assumption that's standard in the literature is what's called strong spatial mixing. Strong spatial mixing, as compared to the weak one, lets me look at influences even when the site that I'm looking at is very close to the boundary conditions. So there's one boundary condition that's common, Xi, and I look at the influence of a flip at Z on this point V. Okay, so the previous setting was when V is in the middle, this decays exponentially. If I also have that when the vertex that I'm looking at is close to the boundary, then I say that strong spatial mixing holds. Again, this won't hold everywhere in my n by n box, so I ask for it in expectation over the random field. So this is more powerful assumption because in some models, like the Potts model, the boundary can actually propagate the influence, but when it's in the middle of the box, there isn't such propagation. Okay. Are there questions? So under this assumption, so this holds for, so again, this holds at all high temperatures by this correlation inequality regardless of what the field is. But also in this the crude arguments part of the picture I said, you can say that if the variance of the field is sufficiently strong, then you have this kind of, even if the temperature is very low, you have this kind of strong spatial mixing in expectation. And the result is that this implies a Poincare inequality with a constant that's actually subpolynomial, so essentially optimal mixing time, n to the little o of 1. And okay, so here actually this gives you a total variation mixing time guarantee and things also. And so you have exponential decay of test functions to their equilibrium values as you'd expect from a spectral gap inequality. Okay, so this is true spectral gap in the form you probably know already. So this n to the little o of 1 is actually an exponential of log n to the d minus 1 over d. And this should be the true mixing time in this model. And okay, we didn't work hard, but we show a lower bound that's exponential of log n to the d minus 1 over 4d. Notice that in true high temperature without a random field, the spectral gap is order 1 and the mixing time is log n. So this says that there is indeed a slowdown when you're in this Griffiths phase. So you have uniqueness globally, but there's small clustered regions that have strong correlations, okay? So we actually can encode some slowdown into those low regimes, but their effect is kind of localized is what this theorem is saying. Are there any questions about that? Okay, so if there's no questions, then I'll say some things about how these kinds of proof arguments go, see the root of this, what's expected to be this true mixing time, and how you like localize these bad regions of small fields. Okay. So let me just give a standard argument that would work in dimension 2. So to show that, okay, first of all, the results are most interesting in dimension at least 3, and this will also show the problem kind of that these small regions cause. So a standard argument for bounding mixing times on lattices is you want to do some kind of multi-scale argument. So you want to localize and say that, okay, so a small region won't really influence other places, and its mixing time is reasonably fast. So what I'll do is I'll take my torus, I'll tile it by order log n by log n by log n, etc. boxes, and because of the fact that I have this exponential decay in expectation, that means, so Markov tells me that there's exponential decay with exponentially good probability for the field. So there's no region of size larger than log n that has bad fields. So there's small regions of size log n that have bad fields scattered around, but none of them are bigger than size log n. So these tiles kind of localize the bad regions. And therefore, if I look on any one tile, there's an exponential decay of the influence from its boundary to the middle. Okay? All of the bad regions are completely confined inside one of these. Okay, so then by a kind of simple monotonicity argument, I can just think about the dynamics which freezes plus on the outside of this or freezes minus on the outside of this. And I do this for every site all around the box. And in the mixing time of those boxes, then I've coupled on the middle vertex because the influence decayed exponentially. So I get some exponential in log, which I can union bound over the whole square. So I get that if the time is more than the worst mixing time of any one of these tiles, then my total variation is less than n to the 10, and I can do a union bound. Okay. So then what's the worst mixing time of any one of these squares? The worst mixing time, this is kind of a classical thing, is exponential in the cut width of the set. And so if it's a log n by log n box in dimension 2, I get exponential in log n, which is polynomial. So that gives me a polynomial, spectral gap, mixing time, everything you want in dimension 2 under the minimal, like, weak spatial mixing assumption. But as soon as I go to dimension at least 3, log to the d minus 1 is super logarithmic, and so this is super polynomial. So it gives us something, but it's not even polynomial in dimension at least 3. Okay? Now, I told you that there are bad regions where you have strong, long range in correlations of size at most log n. So you might be like, well, then that sounds like an optimal bound because these guys have width log n and you can't go any smaller. So why should I expect to be doing any better? Okay, so the low field regions have volume log n. So it might be that they're thin and long, but then they're thin and so their cut width is small. Or they might be kind of square-like, but then their width is actually log n to the 1 over d, much smaller than log n. So, so in either case, by some kind of isoperimetry in ZD, you would expect that the mixing time should actually be sub-exponential in log n. So the isoperimetry tells you the cut width is less than log n, and so if I exponentiate that, I should get something exponential in log n to the d minus 1 over d, which was the true bound that we got. So does that, so this is why one could expect to do better in the model. Are there any questions about that? Okay, so we want to implement this argument and do the localization in a way that depends on the realization of the external field. So the places where there's long-range correlation is a kind of randomly scattered subcritical percolation in my box. There's certain places where it's especially large. I want to pick my tiles according to those regions rather than just as boxes. So the proof structure is basically you want to combine two different types of ideas. And one of them is, based on coarse-graining arguments and things that are typical lattice mixing time types of analyses. And on the other hand, we combined that with ideas from what's called stochastic localization that was introduced by Ronen in around 2013 and really hasn't been used for analyzing mixing times on lattices or things like that. It's much more for mean field models. To reduce a random field model with just the minimal weak mixing to something with like a very large external field. So this first step is going to work when you have a very large variance of your random field. And the second step is going to give you a reduction from the uniqueness to that second part. Okay. Are there any questions? Okay, so let me try and sketch out some ideas from these two. So the first one is going to be much more geometric. The second one, in some sense, more analytic. Okay. So like I said, for the first one, we can assume our random field has arbitrarily large variance, order 1, but very large. You still have these bad regions that are log-sized, where the external field is pretty small.
So for the second step, is this, forgetting how you're doing the scheme, you're not getting a coupling between...
No. So The goal of, so generally, I guess you're aware, but when you do stochastic localization schemes, the Dirichlet form stays decreasing in expectation, and so you want to bound how fast the variance decays. But the real point is that when you do the stochastic localization for the random field Ising model, it stays a random field Ising model, maybe with a correlated field or something, but it's basically doing a jacking up of the external field in a random way. And so you stay kind of within the family of models, just with a higher variance field. And so you can compare a Poincare inequality, a weak Poincare inequality for this minimal assumption to the Poincare inequality for the stronger external field model. Okay, so I want to give a flavor for the geometric step and then a flavor for the analytic step. Okay, so for the geometric step, the goal that we need to achieve is basically come up with a tiling of my domain in a way that the mixing time on each single box is polynomial. So that's what failed in the previous tiling by just boxes. And then on the boundary of these guys, you have some decay of correlations to the middle. So that's, you need to have some kind of decay of correlations to be able to say, well, if I update this box, I couple on the interior of it. And I need an isoparametric condition that, like, there's a lot more boxes or blocks that have a vertex in their interior than that have it on their boundary. So if these are just boxes, this is just, there's r to the d minus 1 many vertices on the boundary versus r to the d on the interior. But once I start making these weirder objects, I need to preserve the fact that their volume is bigger than their boundary. So, so this picture is that if I have a discrepancy here, it doesn't really percolate down into the middle with high probability. Its influence stays localized. And this picture is if there's a vertex here that's on the boundary of this box, there's a lot more boxes that have it on its interior.
It should be the other way around.
Which one? Yes, much bigger. Sorry. Thank you. Yeah. The point is, when it's on the boundary, when I update that box, it creates discrepancies. You're trying to do some path coupling. When it's on the interior, it gets resolved. Okay. So this is then kind of a, I throw down a random field, and I just want to construct such tiles. Now there's not really any dynamics involved. How do I do that? So if you just try and say, well, let's threshold the random field and enlarge by some amount that's like a large constant, any large constant will make the subcritical percolation supercritical, and so that's not going to localize anything. And so what we do is you want to do some kind of multi-scale coarse graining of the field to look for regions that are like especially bad and coarsen them. So what I'll do is I'll call a box good if it has this strong decay of correlations property, from its boundary to its interior. And this box is going to be some big R. So these are truly boxes. These are just box, box, box. And what that leads me to is it goes from this subcritical percolation to a bigger scale where the probability of a box being bad has become much smaller than the probability of a single site being bad. Okay, so this is kind of boosting your percolation probability and getting you bigger boxes. So this is, if I do this, this is now very subcritical, and maybe it's so subcritical that even if I enlarge these bad regions by 1, they don't percolate, okay? And so what I'm going to do is I'll take as my tiles that satisfy properties 1 through 3 in the previous step, basically, the connected components of bad regions in this picture to the right, enlarged by 1. And that's not going to percolate. They're all of size log n, etc. So this seems to have died. Okay. So I take my width r to be, let's say, some log n, something slowly growing to infinity. And this is so that when I update a box, the worst size of it is log n. So exponential minus log keeps the interior isolated from the boundary. And then my blocks are in the good regions, they're just good blocks. But in the bad regions, they're like connected components of these bad coarse-grained sets. So this kind of coarse-graining has been used a lot in equilibrium estimates, and it was very helpful here to go from what would be typically percolating to boosting the percolation probability so that you can kind of isolate regions. Okay. So that's the geometric aspect of the argument. I guess this is really just to give a flavor of how this isolating bad regions is done. And then what you get is that the largest such bad region has maybe volume log n, but you just use isoperimetry in ZD to reason that its cut is log n to the d minus 1 over d, and so that gives you the subpolynomial mixing time bound that we have. Okay. The analytic side of, so actually this is basically sufficient to give this full spectral gap of this e to the n to the little o of 1 when you have this strong spatial mixing, so this strong form of decay of correlations along boundaries. So the analytic portion of the argument comes in bringing this down to the weaker assumption where I just tell you that a vertex doesn't feel influence far away. So, okay, so for this, maybe even if you want to forget the results, here's a nice, what is stochastic localization? Maybe a lot of us have heard the term but aren't really familiar with what it is. So, so stochastic localization in the context of the Ising model is basically a stochastic process in the space of measures where I'm doing random linear tilts to my Ising measure. Okay, so mu0 is just the initial Ising measure I start with. And what I'm going to do is over time, I'm going to basically add an external field because a linear tilt of the measure is just an external field in the Ising model. So I'm going to add a random external field. And where's that random external field going to point? It's going to point in t times some sigma star, which is a sample from the Ising distribution itself, plus a stochastic part that makes it a random tilt. But if you think about this as t is going to infinity, the field is just pointing you towards a single sample from the Ising measure. And so what that does is it localizes your distribution around a Dirac mass at a sample from the distribution itself. So I draw a sigma star from the initial measure, it's that point, and then I kind of randomly localize this measure around that point. That's what the stochastic localization process is. Now, the nice thing is, when we're working with random field Ising models, this is a random field Ising model. And as t gets larger and larger, the variance of the external field is bigger and bigger. And so I have a method to handle large external fields that was this kind of geometric argument using these tilings, these kind of lattice methods. The stochastic localization lets me get up to a sharp threshold by boosting it from just a uniqueness assumption or a weak spatial mixing assumption to a large field model. So let me give a flavor for how this kind of localization is helpful for mixing time bounds and things. So the upshots of this process that have been used to great extent for bounding mixing time spectral gap for spin glasses in recent years, and also for very different contexts like slicing and KLS that are not related to Markov chains, but where stochastic localization has been helpful, is the following set of the observations. So under this process, the Dirichlet form is a super martingale. So what that means is, as I'm localizing my process, if I want to get this Poincare inequality, one side of that is behaving monotonically, at least in expectation, in the way I want it to. Okay? So the Dirichlet form's moving in the right direction, and I'm staying in the family of random field Ising models with a growing field variance. So I have a Poincare inequality for the T large model. The only thing I need to say then is that between the initial time and t large, when I have a bigger field, the variance didn't decay too much. In the spectral gap, you have like the variance on one side and the Dirichlet form on the other. So the Dirichlet form I have a monotonicity property for under this flow. I just need to say the variance isn't decaying too fast as I'm localizing. Okay? So this follows from the next piece of nice stochastic calculus, that if I look at the variance of a test function along this localization process, its time derivative is lower bounded by something that has the covariance of the measure in it. So when I'm in high temperature, covariance of the measure is bounded. The covariance matrix of the measure is bounded. This is like a Dobrushin type of assumption, things like that. And so that means that the high temperatureness of the measure, if it's true along the whole process, along the whole set of times, is giving me the lower bound I need on the variance decay. So this can be used to say that if I have a general Ising model with under let's say a Dobrushin condition, or whose matrix norm is at most something, or covariance matrix is bounded, then I have a spectral gap with exponential in the covariance matrix, just basically from the two slides that I said right now. In our setting, at initial time, under this weak mixing in expectation assumption, the covariance matrix isn't badly behaved. It might have some logarithmic growth because of these small regions that have strong correlations, but in general, the covariance matrix isn't too large. Okay, so the tricky part is showing that along the stochastic localization process, you actually maintain this, because we're moving through a space of random field Ising measures, and it's not clear that they have their covariance matrix bounded by the initial one. So here there's a nice use of FKG plus Ito that actually tells you that in the Ising model, if I run this kind of random external field stochastic localization process, correlations, point-to-point correlations don't decay in expectation. So they don't, I'm adding a random field on top of an initially random field. So this is not something that's covered if you know the Ding-Song-Sun inequality. But in expectation, point-to-point influences only decay with the introduction of a further Gaussian random field. Okay? And so that tells me that more or less I can control this covariance matrix along the stochastic localization process, and that gives me a lower bound on the decay of the variance. Of course, I only have probabilistic bounds on this because this is a random process moving through the space of measures, and if the temperature is lower than the critical one, this might hit, by chance, a set of external fields that has covariance matrix of size n. And then my spectral gap blows up like exponential n. So that would be catastrophic for this. And that's what causes us to have to do this Holder bound to end up with a weak Poincare inequality instead of the strong Poincare inequality. So there's an off chance that something bad happens as we're moving through this space of measures from weak mixing to strong mixing. And in that case, we have absolutely no control because the zero field model has an exponentially large rate of relaxation to equilibrium. Okay, so I think that's all I wanted to say. So thank you very much.